Yes, I think it's yes. There is no need to introduce our first speaker, Yuval Paris. I checked. This is true. I just typed this morning Yuval Paris, Wikipedia. It exists. No, but in German. Okay, so I said yes. I'm really, let's say it's so. Also yes, Yuval is exceptional here, because he is the only speaker who didn't provide the abstract of his talk. And so I'm really intrigued by the title of the talk, that as well, hopefully, as you are, and possibly as the speaker is himself.
Thank you, Sergey. So, it's a real pleasure to be here at the Institute. Decided to survey here two different but related topics that involve the structure of huge graphs. The perspectives are different. So in one of them we look at at one of them we look at a given graph. Though here models of random networks give some of the most interesting examples. So we look at a given graph, and to think concretely, think of a graph with 100 billion vertices. You have one vertex, and you're trying to find somehow a community of this vertex of size 5,000. So what do we mean by that? Maybe some set containing this vertex, which has sparse cuts, a small boundary, few edges from this set to the outside relative to the number of edges inside. Okay? So this is a classical problem, this sparse cut problem. There are many methods, but the new spin on it, which arose in the last 6 years, is locally finding sparse cuts. That's why I gave you the example of these numbers. So we'd like to do something like that and the amount of work we want to do should be about the 5,000, the set we want to find, rather than the 100 billion size of the graph that this vertex is embedded in. So it was quite surprising for many people, including for me, that there are methods that can do that. They can't find the sparsest cuts, but they can find good cuts with provable guarantees. And this was initiated by Spielman and Tang in 2004. What I'll show you is that the method that was initially developed for a completely theoretical purpose, the evolving sets method, can be used for this kind of algorithmic purpose. So that will be the second half of the talk. And what you see here is a simulation of this evolving set. So that's a process which creates random sets that tend to have these sparse cuts. So typically, this set has a small boundary compared to its volume as constrained by the graph it's in. So I'll tell you more about this in the second half of the talk. So I'll stop this and go to the first half, which is the structure of random graphs, a well-studied subject, in particular with a history here in Cambridge. And this is about random graphs. And of course, like many of us here, I first learned of this subject from Bella's wonderful book. Okay, so let me start. So first, kind of general background is that we're going to be finding expanders inside our graph, and one definition of expander is small boundary to volume ratio for sets that are less than half the graph. Another is that the simple random walk on the graph, viewed as a Markov chain, has a spectral gap. So when talking about expanders, we should always think of a sequence of growing graphs, and we want in this sequence that the second eigenvalue, lambda 2, will be bounded away from 1. In other words, there's a spectral gap bounded away from 0. So, so here's a topic which at first seems different from just the structure of random graphs. It's a topic that has been studied and mentioned in this workshop. So this is random metrics on graphs of first passage percolation. Start with a graph K, put exponential weights on the edges of K. What does this metric look like? And there's been a lot of study on that by many people, in particular Svante Jansson, Remco, and their co-authors. And kind of questions that are studied here are diameter, typical distances, and so on. So let me first tell you a little bit about this for the simple model of the random three-regular graph. So these are known results about this model, and then I'll tell you the new thing, which is how they are related to the structure of the classical Erdős-Renyi random graph. Okay, so so take a random cubic graph, so random three-regular graph, and here's a simulation of that. And so when you have n vertices, first suppose that you don't have weights, so the edge lengths are 1. Then this graph, because around most vertices it locally looks like a tree, then this tree has degree 3 everywhere. So in other words, you have binary branching if you move forward. So with that, it's easy to guess and not hard to prove that if you choose 2 points at random, their distances of order log base 2 of n. And here there's no weight. But not only for typical points, also the diameter is order log 2 of n. So there is a difference in higher order corrections, but if you're just putting weight 1 on all the edges, then all the distances here are concentrated at log base 2 of n. Now we change things by putting exponential weights on the edges, and that changes matters. So the typical length, so if you choose 2 vertices at random and look at the and look at the distance between them, then there are now 2 ways to measure it, and we're going to take these 2 points and take the lightest path, so the one with the smallest sum of weights, the shortest path in the new metric. Now this shortest path, what is its length in terms of number of hops? It's now become larger. Instead of log base 2 of n, it's asymptotic to 2 log n. So, but the typical weight of the path, the distance in the new metric, is smaller. It's asymptotic to log n. And finally, you can ask for the diameter here, and so you take the 2 points that are furthest in this metric, and that scales like 5/3 log n. So all right, so I won't go into these calculations, but let me quickly say where the 5/3 comes from. Where is the difference between log n, which is the typical distance, and 5/3 log n? So that difference just arises from the fact that you choose 2 vertices which locally the edges near them have large weights. How large could the weights be? Well, the chance that the weights are each of the 3, this is degree 3 graph, so 3 edges coming out, the chance that the weights are bigger than 1/3 log n is n to the minus 1/3 for each weight. So if you have 3 edges like that, it's 1 over n. So the number of such vertices where the 3 edges coming out are all bigger than 1/3 log n, that will be some Poisson variable. So by changing the parameters a little bit, you can ensure that such vertices exist. And then you take 2 such vertices, you get it takes from each such vertex 1/3 log n just to go to the outside world, and you have 2 of those. And then once you're in the outside world, you're at a typical location, and 2 typical locations, as I've asserted, have distance log n. So that's this 5/3. Okay, so what does it have to do? So now let's scale back to the classical model, and I'll connect this story in a few minutes. So take the classical Erdős-Rényi random graph, GNP. So can be thought of as start in the complete graph on n vertices and do percolation with parameter p. We're going to be interested in the behavior around the critical point 1/n. And there's the phenomenon that a well-known change of behavior for C/n with c less than 1. The behavior is logarithmic, which is some known constant that depends on c. For p of the form C/n with c bigger than 1, the size of the largest component is linear. So we're looking at the largest component, C1. And at criticality, the order is n to the 2/3, actually multiplied by a random constant. So it's the size of the largest component is not concentrated at criticality. And that's true not just at 1/n, but throughout a critical window, first discovered by Bella, which is this window is when p is of the form 1 plus epsilon over n, where epsilon is order n to the minus 1/3. So this has been studied a lot, and we were focusing on understanding geometric parameters like diameter and mixing time of random walks. These parameters have only been understood in the last few years, even in the supercritical case, but we're interested in behavior near criticality. In particular, the most interesting phase for us is the phase emerging from the critical window. So p still has the form 1 plus epsilon over n. Epsilon tends to 0, but slowly. So epsilon, remember, is a function of n. It's going to tend to 0, but epsilon cubed times n will tend to infinity. So epsilon is bigger than n to the minus 1/3. That ensures that we are outside the critical window. And so this is where we're emerging from the critical window, and the large component becomes a true giant. That is it. So one thing about this, that at criticality, the largest component and the second one are of the same order. They're all n to the 2/3, and the third and the fourth, they're just different random constants in front. Once in the supercritical phase, you have this linear component, linear giant, and the rest are logarithmic. So we want to understand the transition between these, the time that the giant component really distinguishes itself from the rest. So that was the reason for this title, Anatomy of the Young Giant. And you'll, by the way, everything here is found in a paper we have on the archive. So if you want to see more details, find them there. I said, so the most commonly, there are lots of aspects studied, and I'm not doing justice, so you can find in the books on random graphs. But besides component sizes, one things we look at here are distances in the graph, expansion, and especially parameters of the random walk, so mixing time. And we've also looked at cover time, though I won't have real time to get into that. So what about the diameter of the component? So diameter of the component has been studied a lot for the graph in the supercritical and subcritical phases. And in both cases, it's if p is 1 plus epsilon over n with epsilon now fixed, not going to 0, so you're either subcritical or supercritical, the diameter is log n, but for different reasons. So in the subcritical regime, again, there are very precise results by Wuchak that tell you the asymptotics in front, but basically the component, one thing I should stress, in the subcritical phase, the components are all logarithmic. If you look at the largest component, that one will have logarithmic size and diameter square root log n. but there is another component which is smaller than the largest one in terms of volume, but has diameter log n. So there are many logarithmic components, and if you try to maximize volume, you'll get actually a random tree on log n vertices, so its diameter will be root log n. But if you try to maximize diameter, you will find even paths of length order log n. So that's the subcritical case that was well understood before. In the supercritical case, the diameter is also log n, but for a different reason, that the graph looks like an expander on a linear size. So that gives you a diameter of log n. And then there are some small bushes attached to it, which are also logarithmic. So they add another factors of constant multiples of log n. One thing is that when you want to make this precise and approach the critical regime, you have to make this decomposition very precise, and that's what I'll be coming to. So that's the diameter. Now what about the mixing time? So here I should say the historical order is the mixing time. So what can one say? So in the subcritical case, in the subcritical case, again, if you look at the largest component, it will be a tree of size log n and diameter root log n. So the mixing time there will turn out to be log n to the 3/2. But there will be this component which is essentially a path of length log n, and there the mixing time will be log squared n. That's the subcritical, that's easy. Now the supercritical case was harder, and it was done independently in two papers, one by Funtulakis-Reed and one by Beniamini, Kozma, and Wormold. These papers, although one of them has just appeared, they're actually written, and the other I don't know where it's appearing, but they were actually written around 2005. So these go back to 2005. Now, in these papers, there was also a conjecture that at the critical case, the mixing time will be a power law, but the conjectured power was not right. It turns out that the mixing time is order n in the critical case. This is in a paper that already appeared a couple of years ago with Asaf Nachmias in Annals of Probability. So, before going on, I should say that these two papers, although they proved, well, the same results, so it's probably right, the methods were different. So, and both were extremely interesting. So, Beniamini, Kozma, Wormold did a very precise, quite precise analysis of the structure of the component. So, they proved some version of saying the supercritical cluster looks like an expander plus trees attached. And then they used that understanding and very simple facts about random walks that they could read off from Winkler and Lova's work to prove the estimate. On the other hand, Funtulakis and Reed used only very rough properties of the random graph, rough expansion properties, not a precise decomposition. But they used innovative results about mixing, refinements of the connection between expansion and mixing to prove their estimate. Yes?
Maybe I'm missing something critical. These are disconnected graphs, so random walks,
only the largest component. I'm only looking at the largest component.
Log square n is not of the largest component. You said it's
yes, it is on. Okay. So on the log squared n is on the largest component in the supercritical. In the subcritical, I'm looking at the random walk on the different components, and I'm asking which component has the largest mixing time. So that would be log squared n. So, all right. So you're right. So here that's right. So on C1, if you define it in terms of largest component, it's actually in the subcritical, it's log n to the 3/2, not. Okay. But in terms of largest mixing time, you'll get log n squared. On a smaller component. Okay, so what happens when epsilon tends to 0? Well, if you use the methods in these two papers, you'll find that the dependence on epsilon is off. So as epsilon tends to 0, you'll get a factor of 1 over epsilon to the 4th there, which didn't matter for these authors because they were considering epsilon fixed, not going to 0. But as we want to refine and let epsilon tend to 0, then the methods here don't suffice. And so here is some graph that tells you what was known. So we're just going to look beyond the critical, so from the critical window and up, and then even the diameter was not known until recently rigorously. So at criticality, the largest component has size n to the 2/3, and with positive probability, it's a tree. When it's a tree, then it's a random tree on those vertices, so its diameter will be the square root of the volume. The square root of the volume, so that's n to the 1/3. It still takes proof, and so with Nachmias, we showed that the n to the 1/3 is true even when it's not a tree throughout the critical window. And as I said, the mixing time was order n. On the other hand, the strictly supercritical case was known, so you have the largest diameter is order log n, the largest mixing time is order log squared n, and to this picture was added analysis by Wuchak and Sandholm, and also by Riordan and Wormald, that proved that the diameter behaves like 1 over epsilon times log n epsilon cubed. So there's a reason behind this number, which we'll get into right now. So in this paper, this estimate was proven up to a constant in Wuchak and Sandholm, and Riordan and Wormald proved an extremely precise estimate with the right constant and even higher order asymptotics almost throughout this whole regime, except for very slow growth of epsilon cubed n. So there was some small region that their initial work didn't cover. For the mix, and in our paper, we show that the behavior is in this intermediate regime, the constant is 3 in front, and we also obtain the mixing time in the intermediate regime. So rather than focus on the values, I want to focus on the techniques that come along. By the way, after we did this, Riordan and Wormald managed to use their method to also complete the picture in the whole region and also obtain their higher order asymptotics in the whole region for the diameter. Okay, so as I said, Binyamini, Kozma, Wormald used in their proof a picture of the cluster as an expander decorated by trees. Now this picture was a descriptive one, so it told you something about how the cluster looks like, but didn't allow you to construct the cluster. If you just look at their result and you want to construct the distribution of the cluster from that, it doesn't give you enough information for that. So to get to the near critical regime, we actually construct an equivalent graph model, which we show is contiguous to the largest component of the random graph. So, and we should give credit. We use a lot of the previous analysis of the random graph, in particular, a very fine local CLT by Patel and Wormald. Okay, so here is our structure theorem. Again, there are lots of results close to this in their nature, though they're not previously proved, though they're not as detailed as this one. So to describe the results, it's easiest to describe in the regime where it's just emerging of the critical window. So what I want to assume here is that epsilon, right, so P is 1 plus epsilon over n, and epsilon is bigger than n to the minus 1/3, but smaller than n to the minus 1/4. And here by bigger, let me assume that the ratio is going to infinity, and by smaller again, this ratio is going to infinity. Okay. So in this is a regime where the result is not restricted. This is not a restriction here, but it just makes the result easier to describe if we're there, because then so what is the known kind of basic decomposition of these kind of graphs? From these graphs, one classical definition is the two core. So the two core are just the if you want the union of the edges that are on cycles. And again, we're just going to look at the two core inside the largest component. There can be two core outside as well. So there's a two core, which you see in this picture. So this is, and the two core can be defined by starting with the graph, removing leaves, removing vertices of degree 1, and iterating until there is no more vertices of degree 1 to remove. So that's the two core. So in this regime, there are no vertices of degree 4. So the two core looks like vertices of degree 3 that are connected by various paths. Now if you take each of these paths and shrink it to an edge, you get a new graph that's called the core. Okay, so that's a classical decomposition. Now what we do is go the other way and construct the graph by starting with constructing the kernel. So just take, in this case, just take a random 3 regular graph on n vertices. So n here is going to be even and will be of order 4/3 epsilon cubed little n. So you start with a random regular graph on this, and for this we have Bella's wonderful configuration model that allows us to understand very well this 3 regular graph. Okay, I write n is of this size, but in fact n has Gaussian distribution with known mean and variance that give it this size. So we can construct it. It's not just a description, it's a construction. So you take some Gaussian variable and take its integer part. I'll say this more precisely. Then how do you get from the kernel to the two core? We're reversing the usual process by going the other way. So you replace every edge by a path of IID geometric length, geometric with parameter epsilon, so mean 1 over epsilon. So all these are IID. So geometrics with a large mean are very well approximated by exponential variables, and that's the connection to the previous discussion of taking a regular graph and putting an exponential metric on the edges. Finally, to get the whole component, you attach a Galton-Watson trees where the offspring distribution is Poisson with mean 1 minus epsilon. And all of these are IID. So we're really happy with this because it's the simplest, most independent construction you can have. Now, to be honest, this is not the distribution of C1 in the random graph. This distribution is contiguous to that one. So let me make that precise. So here's this property here. So we construct a graph C1 tilde using the process I told you, and any almost sure property of this graph, any asymptotically almost sure property of this graph will be shared by the largest component in the random graph. So if you have any property of graphs where the probability is going to 0 for C1 tilde, then it will also go to 0 for C1. So passing to the complement, if you prove that something happens asymptotically almost surely, in this model it will also happen for the random graph, for the largest component. So that's this notion of contiguity that has, of course, been used before. So here is the more precise version of the same statement. So C1 is contiguous to C1 tilde. The size of, so K is a random 3 regular graph on 2 Z vertices where Z is normal with known mean and variance. You replace edges by IID geometric paths and attach IID Poisson Galton-Watson trees. Any question about this?
The tree you attach doesn't depend on whether you're at a vertex or at an intermediate node.
That's right. IID. Yeah, it doesn't depend. Okay, so so our proof of this is still quite involved, and it relies on earlier work by Jung Han Kim on called Poisson cloning. So, given the simplicity of the final statement, I still hold hope for a simpler proof of this. But right now our proof is somewhat complicated. But once you have this structure, then it's very easy to read off key features of the graph, many that were known before and some new ones as well. For instance, the size of the 2 core is 2 epsilon squared n. The size of the kernel, what's the constant that multiplies the epsilon cubed n. The maximal length of a 2 path in the 2 core, so you want a path that doesn't have any branching in it. If you look in terms of GNP, one can do that directly, but there's a bit of work involved. Here it's just the maximum of a collection of geometric random variables. So what's the max? So we know how that behaves. It's just their mean times log of the number of variables involved. And to understand distances in the 2 core, typical distances or maximal distances boils down to the first passage percolation problem I mentioned before, because the 2 core is basically looking like a 3 regular graph stretched by random exponentials, or more precisely random geometrics, IID. So the studies by, for instance, in this paper, can be directly by Bamidi, Hugmistra, and van der Hofstad, can be directly applied to understanding the structure of the random graph. And here's an extension that I'm not going to flash, but everything can be extended beyond this realm when epsilon is bigger than n to the minus quarter. And in that realm, the only difference is that the random 3 regular graphs gets replaced by a random graph with known degree sequence. And the construction is very similar, though a bit more technical, and I won't go into the details. But everything of substance can be understood in this regime, and then just extension is routine. So in particular, from these things, we easily get read-off results like the diameter, which is quite hard to do directly. It becomes 3 times 1 over epsilon log epsilon cubed n. The diameter of the 2 core has a 2 here. And if you look at the maximal distance between vertices in the kernel, so vertices of degree 3, that's where this 5/3 comes in. Okay. Finally, the structure theorem, our whole motivation when we started this project was to be able to analyze the mixing time. The structure theorem, which in the end is certainly of interest in itself, was needed because we had no other way to get the precise mixing time. Here's another formulation of the mixing time result. Look at the parameter lambda, which is epsilon cubed n. So inside the critical window, lambda is bounded. Outside the critical window, lambda is tending to infinity. But since we're assuming it's subcritical, then lambda is still lit O of n. So the mixing time of the lazy random walk on C1, so to avoid periodicity, we stay in place with probability half and move with probability half. The mixing time is n over lambda log squared lambda. And this kind of formula nicely interpolates because before we had 2 different behaviors. We had log squared n in the supercritical regime and n in the critical regime for the mixing. The very different behaviors. How does one interpolate between these behaviors? And here is the answer, very clean formula, n over lambda times log squared lambda. So you see that if lambda is bounded, then you are in the critical window, and this formula holds you get an n, while the other extreme would be if lambda was order n, and then this n over lambda is a constant, and you get log squared n. This interpolates between these, but this is true for all lambda interpolating between these behaviors. Any questions? Okay, so that's all for this part of the talk. The main reason maybe I'll go back. Main reason I emphasize this structure theorem is that, I mean, we have some is just to remember this picture. We have some further applications of this picture beyond the diameters and the mixing times, but I'm sure many of you working on random graph problems will have other questions which, one of the possibilities is to study these questions using the structure theorem. And although here I described the nearly critical case, there is a version of this also in the fully supercritical case where, so again, Beniamini Cosma Wormald had some variant, and one can strengthen the result to give a full description also in the supercritical case. So this you may have other applications for it. So let me move to the second part. Okay. Second. This is joint work with Reed Anderson, also at Microsoft. And so here we're going to change point of view. We'll have a graph that's given to us. It could be selected by some random process, but we're not assuming that. And we're going to find sparse cuts. So since this work was done at Microsoft, I flashed some applications for you, which indicates what kind of graphs we're interested in applying this to. So, 30 million is the smallest we're willing to consider, but as I said, typically 100 billion is what you should be thinking of as the size of these graphs. But besides just thinking of the web, another very interesting graph to look at, which we have the data for, is the graph connecting advertisers to keywords that they choose to advertise on in the search engine. Okay, to show you the pictures though, I'll have to choose something more visual. So this is a random geometric graph that you've seen before here. You just throw down points at random and connect them if they're closer than some delta. So a sparse cut has a low conductance. So here I don't mean electrical conductance, but the ratio of the number of edges connecting a set to its complement to the volume of the set. And by volume, we mean the sum of degrees in the set. Okay, so that's our criteria for sparse cut is low conductance. And in all these examples, this is meaningful, say, in the as some kind of community in close-knit community in a graph. There have been a lot of approximation algorithms for the sparsest cut problem. It's NP complete, so you won't find the exact optimum. But to approximate, there have been many methods, spectral and others. And the best that's obtainable in polynomial time is this Aurora Rao Vazirani. However, all these algorithms are looking at the whole graph, so their complexity will be at least n. So here we want algorithms that will look only at some part of the graph. So the question becomes a local partitioning question. This was.
So are you going to explain the notation now? What does
Sure.
phi to phi root log n mean?
Okay, thanks. So thanks. Sorry, I didn't say that. So so I said you cannot find the sparsest cut. So this notation means suppose there is some wonderful cut with conductance phi. Phi is small for this to be a good cut. We can't find that, but we want to find a good cut, and how good it will be have conductance which is bounded by some function of phi. this function had better tend to 0 as phi tends to 0. So this is an example of what spectral partitioning gives you. Is it gives you approximation guarantee of root phi. There is this wonderful cut of phi. You won't find it, but you find some cut
And you
guaranteed.
can do it in polynomial.
Yes, yes. You can find in polynomial time a cut of quality root phi. And of course, in many of these examples, on random instances, the performance is better than the guarantees. These are the approximation guarantees that will hold in every graph. So, okay. So again, the local partitioning, as I said, will find a sparse cut near a given target vertex, examining only a small part of the graph. And this, again, if you have that 100 billion vertex graph, you have to do something like that. And it was natural to me that, well, this is something that, you know, in practice you have to do by some grubby heuristic, but how could you ever prove a theorem about something like that? So I was surprised that one can prove something like that. I'll come to that in a moment. I mean, here's, you know, one example related to this advertisers keywords graph. So an edge between them means there's a bid, and a community in this graph will indicate some kind of joint interest of all these advertisers, like flowers in the San Francisco area. So the local partitioning is different from the global in that, I said, the running time should be independent of the size of the graph. Well, actually, we can't achieve that, but it's only logarithmic in the size of the graph, which is good enough. And I said there are various applications for this. Besides the ones I mentioned before, there's also an application when you iterate this algorithm again and again, you can do a good partitioning of the whole graph. So, of course, then you'll have some larger complexity. So for finding balanced cuts, you apply this algorithm as a subroutine. So I won't be completely formal, but a little formally, you know, local partitioning algorithm, it takes as input a starting vertex and a target conductance. It outputs a set S, which is supposed to have, if not that target conductance, some function of it, and it does some work, W, and in both the output and the work are random variables. We want that the ratio of W to the volume of the set we find should not be too bad. So the expectation should be bounded by some mild function of phi. And we want to get a set with conductance less than this target phi with, so we can't get a set with conductance less than phi. What we want is a function f, so that if there is a cut with conductance phi, we'll find some set with conductance less than f of phi with substantial probability. And this substantial probability, it's not in terms of the graph, it's in terms of our randomized algorithm. So once this probability is at least a half, we can just iterate this several times to get probability close to 1. And so this was, as I said, started by Spielman and Teng in 2004, and was improved by them and also by in a paper of Reed Anderson and Fan Chang and Lang, and all these earlier papers depended on the following idea. You run a random walk starting from your target vertex, either run it in practice or compute transition probabilities for a random walk. But the random walk is modified in the same spirit as PageRank to occasionally jump back to the starting vertex. And if you stop this random walk at the right time, which you have to plan carefully, then you look at the set of vertices with a large enough transition probability, and that will be the set you use. the parameters of how long to run the random walk and when to jump back had to be tuned quite carefully in these works. Here we take a different approach. It's related, but we just run one Markov chain, the evolving set chain I'll tell you about next, and basically look at its output, and that's the set we'll want. So the improvement on the previous algorithms, on the state of the art before was rather small. So if you compare here, the approximation guarantee is the same as the best random walk algorithm, and the complexity is a little improved. Its dependence on phi is phi to the minus half instead of phi to the minus 1. But perhaps the main improvement is conceptual, because the algorithm becomes very simple to run. It's not trivial to analyze, but that's done once, and then to run it is very simple, and I'll explain that. So it's used for balanced cuts, and I'm not going to go into that. So what's the evolving set process? So in these terms, it was studied by Ben Morris and myself in 2004 to bound mixing rates of Markov chains in terms of conductance. So we gave some refinements of earlier work by Kanan and Lovas, and that in turn refined earlier work by Lawler, Sokal, Jerome, and Sinclair. So there's a classic connection between conductance and mixing, but you can get more precise connections if you use not just this set of smallest conductance, but use the conductance profile. So you look at sets of all sizes and ask, for sets of this size, what's the best, or what's the smallest boundary to volume ratio I can get? And if you have all that information, you can get, which you sometimes do, you can get better estimates for the mixing time. And this was first done by Kanan Lovas, and then refined in this work with Ben Morris. The process we use, actually for a different purpose, occurred in a work of Diaconis and Phil from 1990. Though they just applied it to one-dimensional chains. All right. So what's the process? It's a set-valued process. It's defined using the random walk. So given a graph, first thing we want to avoid periodicity issues, so we'll always use as the underlying walk the lazy walk, which with probability half stays in place and probability half moves to a uniform neighbor. Okay, now from this we want to define a set-valued process, and to define this, so how will this set-valued process evolve? Maybe I'll jump ahead and then back. So given the current set S, we'll jump to a new set S prime. It's the following rule. If a vertex is not on the inside or outside boundary of S, then its status will not change. The only change happens along the boundary. And along the boundary, for every vertex, you look at what is the fraction of its neighbors inside S. So look at this vertex A. It has two neighbors inside S and two neighbors outside. But remember that we're doing the lazy walk, so it also has probability half just to stay in place. So overall, if you are at that vertex, the probability you'll jump into S for the random walk is 2/8, right? 1/4. Similarly, for this vertex B, it will be 3/8. For the vertex C that's already in S, the probability it will be, it will jump into S in one step of the walk will be 6/8, remembering the laziness. Okay? Now what we do is we now do a random set where every vertex is in S prime with probability, which is the probability it would jump into S with the random walk. Okay, so that defines the probability of being in. It doesn't actually define the transition, because I didn't tell you how all these decisions are coupled. Right? These are many random decisions you have to make. You don't make them independently. Turns out it's most effective to make them in the most coupled way possible, namely to pick one random threshold. So for each time step, we'll pick one random threshold. These will change with the steps. So we'll pick one threshold U, and it's going to be uniform in 0, 1. And the set S prime or S1 we go to from S or S0 will be all the y's so that this ratio is bigger than u. All right, so we make all these decisions together. So in this picture, this shows what happens if u is between this 2/8 and the 3/8, then B will move inside the set, C will certainly stay inside, but A will stay outside. Okay? And that's the process you saw in the early simulation at the beginning of the talk. Almost, I'll tell you, there's a small correction there. So what happens if you run this process? It turns out that it's a nice, simple exercise to prove that the volume of this set is a martingale.
So if u is less than half, you lose everything you had, right? So
No, not at all. So if u is less than, so let me go back.
oh, because you have
Okay.
additional ways of going
So
in.
first of all, the smaller u, the more you have inside. So, but, okay, so, right now, one very nice property that makes this possible to analyze is that the volume of this set is a martingale. So that's a real nice exercise to verify. What? U is a uniform random variable in 0, 1. And what? At each step you pick it independently, but for each step you use one random threshold U for all the vertices to decide who is going in, who is going out.
The moment of absorption will be probability of what absorption, or it will not cause it to stop.
Yeah. So the process, as I described it, has two absorbing states: the empty set and the whole space. Okay, so you will run to absorption, but you need to change it in a moment because the process tends to, as I define it, it tends to absorb in the empty set with high probability because the volume is a martingale. If we start at a single point of small volume with very high probability, this martingale will converge to 0 rather than to the volume of the space. So one has to deal with that. But before dealing with that, here's another nice property that's easy to verify by induction, which is that starting from x, the probability that y is in ST is essentially the transition probability from x to y in t steps of the lazy walk. So this with a normalization by the degrees. So for simplicity, think of the initial graph as a regular graph so you don't have these degrees. So what this tells you is, it can be thought of as follows. If you look at the distribution at time t of the random walk, it's right. You have some distribution. This distribution is a mixture of these random sets. So averaging over these random sets will give you the transition distribution probability for the random walk. So these two things are very simple to prove, and I'll use this opportunity to advertise this book came out 1 year ago, Markov Chains and Mixing Times. Besides being available from the AMS, it's also freely available online from David Levin's webpage. And there is a chapter there on martingales and evolving sets that does the basics of this process. Okay, so these are things that were crucial in the analysis of mixing time that we use this for. Now, as I said, the process itself is going to be useless to run because it will go to the empty set immediately. But so instead, what we want is to run the Doob transform of this, the process conditioned to absorb in the whole space. Okay? So for any Markov chain, if you have, say, two absorbing states and you condition the process to absorb in one state rather than the other, you get something well known as the Doob transform. So that conditional process is also a Markov chain. In general, it can be, even if you know how to simulate a Markov chain, it might be tricky to simulate the Doob transform. But here there's a wonderful coupling that does it for you. So Let me tell you what that is. And again, that has its origins in work of Diaconis and Phil from 1990, and even some older work. So, but here is how it works in this case. So, let me define a new process for you, which couples a random walk and the evolving set. So we start with the set being a singleton x0 and a particle also at x0. First, make the particle move to a random location just according to the random walk. So xt ignores the set and just makes a step of the lazy walk. Okay, so that's the transition probability. Now we update the set. How does it move? It moves according to the rule of the evolving set, but conditioned to contain this moving particle. So st plus 1 is s prime. And so what are the rules for the evolving set? Right, it's the y so that pys is bigger than u. But we choose u to ensure that the moving particle will be in the set in the next stage. That is, we choose u not in the whole interval 0, 1, but in the interval 0, px prime s. Okay? And that is the same as conditioning the moving particle to stay in the set. Now, since the set is containing the moving particle, it can't vanish. Okay? What is not obvious is that this thing, it doesn't vanish, but what's not obvious is this exactly has the right transition probabilities of the Doob transform, of this process conditioned to absorb in the full space. And that's some kind of magical identities that happen. And again, these, you can find them, for instance, detailed in the relevant chapter in this book. Okay, so once you know that, then there's some easy things that follow. So the probability, so I'll emphasize one, that if you look at the conditioning the other way, condition on the sets S1 to ST in this process, and look what's the distribution of the particle given that the sets were S1 to ST. Well, the answer is the particle just has the stationary distribution restricted to ST, so just the distribution proportional to the degrees. In other words, you can get, if you're interested in getting a pick from the stationary distribution, you could run this process till absorption, and then, so with the coupled process, the particle and the set, and then when the set absorbs in the whole space, the particle has the stationary distribution. Okay, so I'll have to go quickly through some of these technicalities due to time, but the transition probability kernel for the volume biased evolving set process is just the original transition rule. K is the transition rule for the ESP, and you just bias it by the ratio of the volumes. That follows from the martingale property that I mentioned before, and that's why I said this is equivalent to this Doob transform conditioned to absorb in V. So here is simulation of how the set looks like in various steps, and here there are some precise theorems that give you the guarantees on this set. So I don't have really enough time to go in detail into these, but again, the paper is available on the archive, and so I'm going to focus on just one explanation of why this algorithm achieves an improvement over previous ones. So the analysis involves some tricky martingale estimates that I don't have time for. So maybe one more point I want to emphasize. What's the connection of this algorithm with conductance? So if you want to see how fast this random set moves, it depends on the conductance of the set that it's at. So so if this uniform variable is less than half, the expected volume is going to grow by the boundary of the set. And if you condition on this variable to be bigger than half, the expected volume will decrease by the boundary. So the movement of this martingale is determined by the conductance of the set that it's at. So I'll have to again skip this and emphasize that the improvement in complexity comes from the fact that in this algorithm you only have to keep track of the boundary of the set. So all previous algorithms kept some kind of vector of weights. say, transition probabilities for random walk and modify this by, say, matrix multiplication. Now, even if the weights from time t to time t plus 1 changed very little, you still had to keep track of them. But here, we keep this random set, and all that can change is its boundary. And there are two cases. If the boundary is very big, the set moves very fast and we're happy. If the boundary is small, then, well, we're moving slowly, but we're only keeping track of the small boundary, so we're still relatively happy. And that's where we gain compared to the
square root.
Hence the square root, yes. Okay, and again, due to time, I'm going to have to just cut to the pictures of this at various stages and maybe end with something. So we've done various simulations comparing the performance of this to the random walk algorithm. So besides the performance guarantees, also in practice it seems to perform a little better than the random walk algorithm. So here in this picture, the blue is the random walk algorithms. We're trying to get the smallest possible conductance for a given size, and the red is the evolving set construction. And whenever the blue finds a good cut, which are these minimum, then the red finds something as good or a little better. Of course, that's just one simulation. We have more extensive ones. The improvement, isn't dramatic, so there's small improvement. But the simplicity of the algorithm is you have this. There is no special parameters to tune except when you want to stop. You run this algorithm. You observe what you see along the way. When you're happy, if you're happy, you stop, and that's the algorithm. The analysis is intricate, and that's what I was kind of skipping over. And I end with just this picture. These are the weights that had to be developed for the early algorithms. This is the evolving set process, and this is the boundary that we need to keep in the efficient simulation. Thank you for your time.
About the first part, can you prove asymptotic contiguity of the two different giant components? Can you also prove asymptotic equivalence?
I don't know if it's harder, but it's probably as hard, and we were exhausted by the time we proved contiguity. So I guess that contiguity also holds in the other direction. So there is this asymptotic equivalence, but we didn't prove that. So that's still for the applications.
Asymptotic equivalence, you would be able to push weak convergence too, whereas with asymptotic contiguity, you can only push convergence and probability.
So by asymptotic, I don't know what you mean. So asymptotic contiguity.
Asymptotic equivalence, I mean that the probability of any event is asymptotically the same as
Up to
no constant.
No, that doesn't. Okay, this I didn't understand what you meant. No, that isn't true.
That isn't.
That isn't true. So the probability isn't the same, and it's probably not even, the ratio isn't even bounded. So the probabilities could be, at least what the proofs gives is that if you have a low probability event on one side, the probability on the other side could be square root of that. So it really only tells you if you prove some almost sure property for our simple model, this C1 tilde, then this almost sure property will also be satisfied for the random graph. But what I said should also be true is the same kind of contiguity in the other direction. We didn't have an application for that because I don't expect you'll want to prove something about our model by going through C1. But it's still interesting to prove contiguity in the other direction, just so you know that we're not missing any property of C1 with this model. We haven't done that.
I was just wondering if there was meant to be any connection between the two parts of your talk.
The speaker.
Apart from the speaker, right? Did you use the techniques in the first part for the second part?
So there was some connection in the kind of the composition ideas, but not at the technical level. Yes.
In the second part, I mean, is there a way to use optional sampling theorem to get like the first set which would have cut with this or that property?
So So in the proofs, we use optional sampling all the time, of course, and Doob inequalities and so on. So what kind of property would you be looking for? I mean, we were focusing on just getting the smallest possible cut. So the kind of stopping times we considered are: one, you stop when you run out of time. You stop when two, you stop when you reach the target size you want, and three, you stop when you reach some target conductance. And all of these, can be used. But I don't know what other stopping time you have in mind.
I was just wondering. So I don't know the first set with some size large enough, which has this or that.
Yeah. This is one of the stopping times we use.
Okay.
Could you explain why it was better for when you were making yourself evolving, why you had to
When making what?
your set evolving
Yes.
in the second part? Why did you have to? Why it was more smart to take just a single random variable u and not a random variable for each vertex of the boundary?
Right. So, okay, let me go back to that. Okay. Okay, so all the properties, all the distributional properties would be shared no matter what rule you use for the coupling. The difference is in the rate of absorption. So this kind of coupling minimizes the time that the set takes to absorb. So and so by making the see, if you would make all these decisions independently, the set would grow in some places, shrink in others, and then it would go the other way, and you'd get much slower behavior. So in order to speed up the absorption and move the set faster, you want to maximize the variance of this martingale, and then you can easily calculate what is the variance generally. Right? So roughly speaking, if you have a sum of random variables, you want to maximize the variance. You want to make them as positively dependent as possible rather than independent. And that's what we want to do here, because the rate of movement of this martingale is just determined by the variance.
In particular, the second part. So it's correct that it's another way of perfect simulation of station distribution.
Yes, yes, and
So,
but in this form, it's really equivalent to one used in different language by Jim Phil in the 90s. Yeah. So for the purpose of perfect simulation, these ideas existed before, and that was crucial here. So when you define this, why have the set constrained to contain a moving particle? It may be first most natural to constrain it to contain, say, the starting point. But that doesn't turn to have the right distribution. So there's some magic cancellation that happens when you constrain it to contain the moving particle. It has exactly the distribution of the Doob transform, which is what we want.